So, hello there, my name's Aidan Hogg and I'm from Imperial College London, and today I wanted to present to you an idea. And that idea is to do with segmentation. So imagine if I was to give you an audio recording with many speakers speaking on the audio recording and asked you to tell me how many speakers there were and who was speaking at what time. I'm pretty sure you could all do this with near 100% accuracy. You could tell me how many speakers were speaking in that audio recording. In fact, I think you could do even better than that. You could tell me when two speakers are speaking at the same time. But this is actually a problem that computers find extremely difficult and extremely challenging to solve. And in this work that we've been doing at Imperial, we looked at using pitch to try and help solve this problem. Can we use the pitch of someone's voice to work out if multiple speakers are speaking, and also to just segment when speaker change boundaries happen, when one speaker goes to a new speaker. So this is some work that we presented at WASPAA in 2019, and it sort of builds on some of the work that we presented at ICASP in 2019 as well. So why don't we jump right into it and start off with the motivation? Well, as you can see in this top box here, I start off with answering the question, what is diarization? Well, that's basically the problem I've just described to you. Who spoke when in an audio recording? If you look at this picture here, you can sort of get an idea of what that looks like. So here we've got an audio recording, and what we've done is we first segmented it, that is the dotted lines that you can see on this particular image. And then what we've done is we've coloured in the actual speakers. So there's a blue speaker and a green speaker. So there's two speakers in this recording. In this work, we're going to focus on that segmentation step. So that first step of putting in those dotted lines, and the clustering step of working out who's speaking, we're not going to tackle in this particular work. So some people actually argue, why do we even need this pre-segmentation step? Surely we could just segment uniformly. So we segment maybe every 2 seconds, let's say, and then we cluster, and segments that belong to the same speaker that are next to each other will just get merged together. Now the problem with that is, although it solves the need for the segmentation step before clustering, is you're now working with very small amounts of information, because if you've only got segments of 2 seconds, for example, you don't have much to go on to say what the identity of that speaker actually is. If you're trying to cluster 2 segments together and there's only 2 seconds in each segment, it's quite hard to tell which speaker is speaking. So if we can actually pre-segment correctly on speaker change boundaries, like in this particular example, you might get really long segments that are quite a few seconds long, so maybe 15 seconds. So we've got much more information on the speaker if you've got a 15-second segment than if we've got a 2-second segment. So the idea is try and give us as much amount of information as possible to the clustering step. So that's why we always want to probably do a pre-segmentation step before we do clustering. And that's why we focus on that in this work, because it will improve diarization and performance. The other thing that I should mention is, well, why do we use pitch in the first place? Why pitch? Well, actually, in recent years, the way that this has been solved is through machine learning. And there are some drawbacks to that. The main drawback is you need training, and obviously you need lots of features. So we thought, is there any way that we could just use pitch to solve this problem, rather than training a massive network which requires lots and lots of data, just using traditional signal processing techniques? And we found that actually in this work we can get very good comparable performance to a machine learning technique. Also, we found that pitch actually is a very useful feature to be using in terms of its temporal variations. So normally what you would do is, if you look at this particular meeting here, you can see that there's 4 speakers, and I've given their means in dotted lines, and then you can see their pitch tracks in different colours. Now, normally what would happen is when you train a model, you would do it frame-based. So you would take your bit of speech, you would chop it into frames, and then for each frame you might get the mean pitch, or fundamental frequency we could call it, or you might look at the fundamental frequency variation spectrum and get a feature from that. Now the problem with those is they don't take into account the varying over time nature of pitch. So in this particular case, these methods would work quite well because the mean pitches and the variations are quite different. But if we've got a case where we've got 2 male speakers, for example, and their pitches are quite similar, it'll be quite hard to actually differentiate the two just looking at their mean pitches or their variations. But if we track over time, it's probably possible that we can work out when speaker changes happen based on jumps or changes in pitch. This is actually work that we presented at ICASP. So what we did was we tracked with a Kalman filter, a pitch track, and then what we were doing is we were predicting future pitch values. So we were taking the pitch at a given frame and saying what did we expect the pitch to be at the next frame. If we were predicting badly, if we're getting a very large prediction error, it's probably not because our prediction was wrong, but actually because a new speaker might have started speaking. So when it's the same speaker, it's very easy to track. But as soon as a new speaker starts, it becomes the error in the prediction becomes very big. So we could work out where speaker changes occur based on this error-based approach of predicting pitch. But the problem with that is we only had a single track. So we were only tracking the single fundamental frequency. And as you can imagine, in a lot of cases, we don't have like speaker A, then a pause, and then speaker B. What would actually happen is speaker A and speaker B would overlap in their speech. So speaker A would continue talking even after speaker B has already started. So there's some overlap in the speech. And this work basically says, well, can we look at pitch more to try and solve that problem of overlapping speech? And the way that we do that is rather than just tracking the fundamental frequency, what if we track all the harmonics associated with that fundamental frequency? And that's what we do. So to take you to the method then, first we have to generate our observations. So before, if we were just tracking the fundamental frequency, we would just have one observation, which would be the pitch. But now, because we're tracking all the harmonics, we have multiple observations. And actually we need to work out what are the likely, or what are the possible fundamental frequencies in any given frame. So as you can see here in this toy example, if we just measured from a peak detector 100, 200, 350, 400, and 450, what are the possible observations that we could get? Well, the first thing we do is we remove unreliable detections, and we do that by setting a threshold to this reliability measure, which actually just measures the intensity of the peak. So the peak is not very intense. If there's not much energy in that peak, then it's removed. So you can see that we start off here with 5 peaks, and we remove one, so we end up with just these 4. So now we're left with these 4, 100, 200, 350, and 400, because this value is obviously less than 10. We now need to work out what are the possible fundamental frequencies that could exist for these measurements. And there's 2 possibilities, isn't there? It could be that the fundamental frequency is this green one, which is 100, and then we have the first and third harmonic at 200 and at 400. Or it could be the blue, which is the fundamental frequency is actually 200, and we're just seeing the first harmonic at 400. And we don't know which one is correct, or which one is right. So what we have to do is we have to take both of them as possibilities. So this means for each frame in time, we actually get multiple observations. And therefore we have multiple tracks that we need to track. And to solve that, we now have multi-hypothesis tracking. We can't just have a single Kalman filter tracking the fundamental frequency. We need lots of Kalman filters tracking all of the harmonics. So I'll talk about the Kalman filter in just a sec. But before that, I just wanted to expand how this multi-hypothesis tracking works. Well, you can imagine these little balls as fundamental frequencies for the observations. And you can imagine that in time step 1, we have just one observation, then 2 observations in time step 2, and then, well, actually I've called it time step 0. And then time step 1, we've got 2 observations. Time step 2, we've got 2 observations as well. So now these are the possible observations over time. What are the possible tracks? Well, I've given you one, which is it goes up and then down, and then this track starts here and goes up. Or it could be number 3, which is these 2 tracks here. Obviously 3 is more likely if we just look at it than 2. There's obviously lots that I haven't drawn. There's actually, it grows exponentially with the amount of observations you get in each time step. So if this is the picture over time, and really what we want to do is select 3 as our best solution, we have this multi-hypothesis tracking technique. So imagine this tree structure of all the tracks that get generated with all the observations we have. So we start off with one observation in time step 0, and then there's a possibility that this one observation is associated with these 2 different observations at time step 1, so 0 going to 0 and 0 going to 1. Or that there actually is no observation. The observations are both wrong, and we've indicated that with an X, so that's also a possibility. So we expand all those possibilities, and we also have to assume that actually these two new observations are just part of a new track. So this is tree 2 and tree 3, just assuming that a new track has started from that observation. And then we do the same thing. So at time step 1, we expand all possibilities for each observation of how the track could be progressing. Now, obviously, these tracks conflict with each other because you can't have two tracks using the same observation. That would mean that one observation belongs to two speakers at the same time, which we don't allow. So we have a technique called the maximum weighted clique. And what we've done is we've drawn lines between every track that can coexist together. So these two tracks don't use any of the same observations, so they're joined by a line. Same with these two, for example, and as you can see, all the lines on that particular diagram. But these two, for example, are not allowed. They share an observation. Well, they actually share two, don't they? At time step 0, they share observation 0, and at time step 2, they share observation 1. So tracks that use the same observations can't exist together. So they conflict, and we don't allow them. So now we need to, it's an optimization problem, we need to select the best tracks that don't conflict. Which means that if each of these balls represents a track, and these shows the observations that make up each track, we need to give a weight to a track, like how likely is that track to occur for the optimization algorithm to select the best tracks. And the way that we do that is we use the Kalman filter. So the Kalman filter is obviously doing a prediction at each time step, and that prediction might be bad, or it might be good, and that's where we get a prediction error. Which is actually what you can see over here, this estimation error. And however good that estimation error is, what we do is we average it over all of the timeframes that made up a track. And we say that that's how likely the track is. If the track was built up with lots of errors in the estimation step, then it's probably a very unlikely track. It's probably something like number 2. But if actually the errors were very small, then it's probably likely that it was tracking things quite well, and actually the track is very likely. And in this case, we've selected these two tracks that don't conflict, that would give us a possibility, let's say, like this, where these are very highly likely tracks, or the most likely tracks from the maxi-weighted clique. Nice. So just to explain a little bit about the Kalman filter then, and the most interesting thing to note is, so we have a state space equation, which basically the state space x is just the pitch, or the fundamental frequency, that's modeled by a random walk. And then we have this prediction step. And the prediction step basically says that the pitch at the next time step will be the same as the pitch at this current time step. And we also have a variance, which basically says how good do we think this prediction is. And it's interesting to note this spectrogram over here, because what this shows is that variance over time. Now, as you can see, there's parts outside of the grey boxes where the variance massively increases, and then within the grey boxes, the variance goes down. And that's because the grey boxes represent where voice speech occurs. So if you look at the spectrogram, you can see where there's voice speech, and you can see the harmonic structure, and you can see when there's voiced speech, the actual variance decreases, because we're running an update step, which basically lowers the variance. We can see that here. But if we're just running prediction steps without the update step, then as you can imagine, this just keeps increasing linearly. So we just see this increase linearly due to this equation here. So we're basically saying if we haven't seen an observation for a long period of time, then it's very likely that there's a large error in our prediction. So we shouldn't really rely on the prediction. We should rely more on the observation that we're getting at that time step. But if we've seen an observation in the previous time step, then we should rely probably more on the prediction, because actually there's probably lots of errors in our observations. And if we've just seen lots of observations, then it's likely that our prediction is very good. And actually, if our observation is way off, then it's probably that the observation is wrong. That's what the Kalman gain actually tries to do. It tries to trade off these two. It tries to trade off between the prediction and the observation. So you can imagine if this k vector was all ones, then obviously this would cancel out with this, and you would actually end up just with z, which is the observation. Whereas if this vector k was all zeros, then you can imagine that you would just end up getting the prediction, which is basically the same here, so it just becomes the prediction is the output. So we're trading off between the prediction and the observation. The way that we do that is using this optimal Kalman gain, and as you can imagine, this estimation error is the way that we can select which tracks are the best, because if tracks have been built up with loads of errors, they're very unlikely. This is also good because we actually use some gating. So, or this is doesn't show the whole story, because actually some tracks can obviously die, and obviously we wouldn't expand a track if it's got a very large estimation error. If the track is basically, if an observation is very unlikely to belong to a track, there's no point in expanding it, because if, for example, we have a track down here and then an observation way up here, there's no point in even considering that possibility. It adds to computational complexity for no reason. So, with that all in mind, let me show you some results. I apologise that the camera has obviously stopped working, but hopefully you can still hear me, which is the most important thing. So, as you can see, these results, the white crosses show the possible fundamental frequencies that we generate using the observation generation that I told you at the beginning, the possible observations, and the black crosses show the harmonics related to those possible fundamental frequencies. So let me just zoom in so you can see it maybe a bit more. There we go. So you can see that we get all of these possible fundamental frequencies and their associated harmonics. And then when we run our tracking algorithm, we get these tracks. Now these are two bits of Timmett speech that have been overlapped. That's why they're quite clean and quite nice, because they're anechoic. And you can see speaker A, then speaker A plus B, and then speaker B. So they're overlapping between these white dotted lines. Now the main thing that you can see here, the problem, is we're tracking here the first harmonic, which we don't want to do, as well as the fundamental frequency. And then here, we're tracking the fundamental frequency as well as the subharmonic. So we're getting multiple tracks for one speaker, and some of those tracks might be wrong. So we have to deal with that problem, and we have to use these tracks to try and work out when speaker change boundaries occur. And that's this box down here. So let me just zoom out quickly. So as you can see, this toy example here is basically a replica of this example here, where you have two speakers overlapping slightly. That's what you see here. And then this one is an example of when we've got a pause between two speakers. So let's say we've got speaker A in blue, and then speaker B in green. Then we've got speaker A, then speaker B, then speaker A again. One of them's overlapping, one of them there's a pause. So the overlap, which is in grey, is quite easy to detect, because what we can do is we can say, are the tracks harmonically related? If the tracks aren't harmonically related, then there clearly is more than one speaker. If there's one speaker, then all the tracks should be harmonically related, because even if we select the first harmonic or the subharmonic, it will still be harmonically related. So in this case, these are not harmonically related in this region, so we have overlap. Whereas these three tracks are harmonically related, these two tracks are harmonically related, and these three tracks are harmonically related. So they're fine. But we detect this overlapping segment. And we know that the onset of overlap will actually tell us that there's been the onset of a new speaker. If we currently have no overlap and then suddenly start having overlap, then a new speaker must have started talking. So we're starting to see how we can start to segment. So we've got overlap onsets to start with. Then, to get the case where we've got a pause between the two speakers, like here, what we need to do is we need to actually reduce how many tracks represent one speaker. So you can imagine what we do is we remove the overlapping speech, and what we do is we try to compress the tracks to a best candidate. So rather than looking at all the tracks, we pick the track that we think is most likely to be the fundamental frequency track. And we do that actually using the reliabilities that I showed you at the beginning. So we look at how the track was built up and the observations that we used. And if more reliable observations were used to make up the track, then it's more likely that that track is the fundamental frequency. So now you can imagine that we can compress these three tracks, or these two tracks, down to one, and I put that in bold, so that shows the best candidate for the fundamental frequency. And now what we do is we just run our Kalman filter method that we presented at ICASP to work out when a speaker change happens with this pause. So it's tracking this green speaker, then there's a pause, and then it starts tracking this blue speaker, and what will happen is there should be an error here detected, and a speaker change detected, because the speaker has changed. Obviously, if it's going here, it'll be tracking blue, then there's no speech because we remove the overlap, and then it starts tracking green. We know that this is actually the offset of overlap, so we don't need to include that when we do our complete segmentation, because if a speaker change occurs at the end of if a speaker change is detected at the end of an overlap region, then we know that actually that's the offset of a speaker. So now we have a way of detecting all speaker onsets, and we do the union of those two to get the complete segmentation file. And then we finally compare that with a machine learning based method, which you can see here from the IEEE corpus, which was presented at Interspeech, which basically uses MFCCs, their first and second derivatives, and energy in their first and second derivatives to work out when speaker changes happen. Now, I should explain what a hit and a multi-hit is. So you can imagine that we have Oracle segmentation from the IEEE labels. And what we do is we take that Oracle segmentation and we put a collar around it. So we say if we've got a speaker change, we'll just put a little collar around it of 250 milliseconds either side, and a hit is when we detect within that collar. Whereas a miss would be if we don't detect that speaker change at all within that collar. A multi-hit would be when we detect multiple hits within that collar. We detect that speaker change multiple times within that collar. And then a false alarm is when we detect a speaker change, and obviously there's no speaker change there. So you can see that actually, in terms of hit, we do better than the machine learning based method. And in fact, in terms of false alarms, we don't really do that much worse. The only place where we do worse is the multi-hit, which basically means within that collar we're actually detecting speaker changes more than once. Which isn't so much of a problem, because if speaker changes are detected close to each other, then we probably know that a few of those are going to be spurious and we can actually merge them into a single speaker change. So the fact that our hit and miss rates and the false alarm rate are comparable is what we care about. And in fact, our hit rate is actually better than the machine learning method that's been trained on lots of data, whereas our data, we don't do any training, we just use the pitch, nothing else. So it's surprising that we can achieve such good performance just using this traditional DSP approach rather than deep learning. So that's basically what I wanted to present in this paper. It takes what we did at ICAST, which was looking at whether we can detect speaker changes just using the fundamental frequency of the voice, and looks at trying to track multiple harmonics so we can actually detect overlap as well as speaker changes. And that helps us with the speaker segmentation problem, because now we can detect the onsets of speakers when they start before the offset of the active speaker. So this is a novel approach, and it shows that you can get comparable performance with a modern machine learning approach that we've shown here. Obviously, we're not claiming that you would use this only when you're doing your segmentation. It would probably be part of a multimodal approach. We would probably have to take these pitch tracks and incorporate them into a machine learning method. But it shows that actually taking the temporal varying nature of pitch into account is a really good idea and is really helpful in trying to solve this segmentation problem. Thank you for listening. If you have any questions, do feel free to email me. Yeah, I'm always welcome. I'm always happy to hear feedback, and yeah, do contact me. Thanks.